All right, welcome back. Here's a few sample problems from section 2.2, which is dealing with polynomials of higher degree than quadratics. But interestingly enough, our first one actually that we're looking at today is a quadratic. We're to find all real zeros and determine their multiplicity. Um, there are three ways in a quadratic that are fairly convenient for finding real zeros, and first would be factor, but factoring isn't guaranteed to find all real zeros. It would find all rational zeros if we were good at factoring. We could also use quadratic formula. We could also set the equation equal to 0 and complete the square. Um, I would probably typically not do that unless I was looking for a vertex as well. But let's go ahead. This is easily factorable. So if I take this equation, set it equal to 0, factor this into x plus 5 times x plus 5 equals 0, we would say our solution is negative 5. But when we're talking about all the zeros, we're thinking graph, really the negative 5 would appear twice. So we would say our zeros would be negative 5, and that is multiplicity 2, which tells us that we have a double zero, which means the graph wants to act like a parabola there. So a little bit of review of some graphing techniques we've talked about. We know for sure this graph passes through 25. We know that as it's going through 25, it's going up like a line with slope 10x, really steep here. But we know that it's going to end up looking like a parabola. So it's actually going to get steeper, a positive parabola, and eventually it's going to come back up in this direction. But what we just learned is that negative 5 is not only a 0, negative 5 is the 0. I would write it this way. It's a double. That's a touch point. An analogy that I use, that'd be on another video, this would be husband, wife, brother-in-law. That's husband and wife are home. Friend comes over, and the husband says, come on in. And the wife says, no, this place is a mess. You can't come in here. Go back home. So that's our touch point down here. Again, since it's an x plus 5 squared or a multiplicity 2, that 0 wants to act like the vertex of a parabola. So more to come on that. Okay, find all the real zeros and determine their multiplicity. Same thing. In this case, if I set this thing equal to 0, I'd like to factor. I can factor out a t, and I get t squared minus 4t plus 4 is 0, which further factors into t times t minus 2, factors of positive 4 that add up to negative 4, minus 2 and minus 2, or t minus 2 squared is 0. Therefore, we would say t is 0, t is 2, t is 2. Or we would have zeros of 0. So here's our zeros of 0 and 2, but the 2 is a multiplicity 2. So what's that mean in terms of the graph? Things we know about this graph. Ultimately, it's a cubic. It wants to go up, positive cubic, up to the right, down to the left. We know that it starts at 0. There is no coefficient. There's no ending term. It starts at 0, and it wants to look like a line with slope 4 through that point. We know then it's going to, for a while, try to look like a negative parabola, so it's kind of cupping down through here a little bit. And ultimately, positive cubic. What else did we learn? We learned we had a 0 at 0, but that just confirms what we already knew. We learned we had a double 0 at 2, which makes this guy a touch point, a double 0. It's going to eventually come down to here and head up. There's our graph. The only question we might be is I wonder how high it gets. So we may want to put in 1 for x, but right now all they're really asking for is zeros and multiplicity. I'm kind of leading you to the next step by discussing the graph. Okay, find a polynomial function with the given zeros. Well, if I said that you were to find the polynomial function with these zeros, 4 and negative 3, I would hope that you would say, well, if 4 is a 0, then x minus 4 must be a factor. If negative 3 is a 0, then x minus negative 3, or x plus 3 is a 0. Therefore, if 6 plus root 3 is a 0, x minus that must be a factor. And if 6 minus root 3 is a 0, x minus that. Whoops, this one's 6 plus root 3, excuse me. X minus the 6 minus root 3 must be a 0. So this becomes x minus 6 minus root 3 upon distribution. This is x minus 6 plus root 3 when we distribute. And that could be our function. Truthfully, that's not wrong. However, simplified, this is going to look a little bit nicer. Now, to superfoil this, I realize I've got to take x times 3 things, negative 6 times 3 things, negative root 3 times 3 things. I should end up with 9 terms. You can shortcut this if you want, but I'm going to go through the full process here. I'm going to go through the full process of finding all 9 factors. So I'm going to take x times all of these. I get an x squared minus a 6x plus a root 3x. I'm going to take the negative 6 through. I get minus 6x, I get a plus 36, and I get a minus 6 root 3. And now I'm going to run the negative root 3 through. I get a minus root 3x, a plus 6 root 3, and ultimately a minus root 3 times root 3 is 3, a minus 3. And because we have this conjugate working here, I expect some good things to happen. So what happens? I'm going to bet we got to cancel for that. We do. I'm going to bet we have a cancel for this. We do. So I'm left with x squared. I've got minus, so I've used this term. I've got minus 6x minus 6x minus 12x. I've got a plus 36 and a minus 3 for a plus 33. So there's a function that has those zeros. So yes, this is our function, but most certainly in this we would claim that this guy is more simplified. So this is just really kind of a battle in organization, but one thing you probably ought to check along the way is that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. 3 terms times 3 terms, 9 terms. Okay, find a polynomial function with the given zeros. Well, if negative 5 is a 0, then x minus negative 5 or x plus 5 should be a factor. But this is multiplicity 3, 3 of those. If 0 is a 0, then x minus 0 or x is a factor, multiplicity 2, f of x equals. And that would be it. Notice they say find a polynomial function with given zeros. That would have it. So would this. It would have a different shape, but it would still have the different zeros, this being our most likely response. Pretty easy. Okay, now we are to sketch a 4th degree polynomial with 3 real zeros and a positive lead coefficient. So this might look something like f of x equals positive 2x to the 4th and then some other stuff. But that tells me a lot about my graph. If my graph is positive with an even with an even exponent, positive coefficient, even lead exponent, then this thing wants to rise to the right and rise to the left. That's our end model behavior, or our left-hand, right-hand behavior. Now, I just need 3 zeros. And the temptation is to, I know I got some wiggling to do in a 4th degree. The temptation is maybe just come down. Here's 1, here's 2. I can't go down through again and do something maybe along the line of this. So you would say 1, 2, 3 zeros. However, this guy is really a double zero. Now, we could debate this, but technically, we would say that this is 4 real zeros. An even function can only have, if we're counting multiplicity, an even, not an even function, but an even degree polynomial, which doesn't necessarily have to be an even function. An even degree polynomial can only have an even number of zeros considering multiplicity. We could have 2. We could either come down, touch, maybe get the rest of our wiggle up here. That would count as 2. We could come down, cross, cross, get the rest of our wiggle done up there. That would be 2. But as soon as we touch, we can't cross through again without getting 4. If we touch, that counts twice. That's 4. So again, debatable depending on whether you're talking about multiplicity, but our book would say that you cannot have 3 real zeros. 74. Here we're to sketch the graph by applying the lead coefficient test. Our lead coefficient, we have a negative and a 6th degree. Well, 6 degrees want to rise right, rise left. So I know for sure before I look at anything else that this thing is going to fall to the right, fall to the left. Upon further inspection, I know this guy's going to go through 8. I know it's going to go through with a slope of 0 because there is a 0x term here. I know the next thing it's going to want to do is look like a positive cubic. This thing wants to look like this at this point. That's a lot of information I have there. I've already got my wiggling, I've already got some of my wiggles taken care of. I know eventually we're headed down. We're headed down here. So let's see what happens. After we're done with the cubed, it starts acting like a negative to the 6th. This thing's going to go up for a while. I don't know how. Come back down, go down. I expect there only to be 2 real zeros in this. So that's before we've really done any work in this new section. That's a lot of information. So let's go ahead and look at, can we factor this? Well, I sure don't like this negative. I'm going to take it out. Negative x to the 6th minus 7x cubed minus 8. And then you'll say, well, that's not quadratic. It's 3 terms. I don't know how to factor it. Well, it is quadratic in nature. 2 to 1 to 0 x's. If this was x to the 100th minus 7x to the 50th minus 8x to the 0th, that would be quadratic in nature. So maybe this guy factors into an x to the 3rd, x to the 3rd. Factors of negative 8 add up to negative 7. Negative 8, positive 1. Foil that in your head. We get x to the 6th. We get a plus 1x. We get a minus 8x, sure enough, and we get a minus 8. And then I know we'll have some people out there like, oh, I remember I can factor these because this is the difference of perfect cubes. What's the rule? It becomes a binomial times a trinomial. And we get an x and an x cubed here. With the x, I get the 3rd root of 8, which is 2. I have to take 2 times something to get negative 8. This is a minus, this is a plus 4. And what goes in the middle here is the product of these guys, which I haven't given myself much room for, 2x. Okay, let's take a look at this guy. The sum of perfect cubes factors. Give myself a little bit of room over here. The sum of perfect cubes factors into the similar. A binomial, a trinomial. This is going to be the x. This is going to be the 1. This is going to be the x squared. This is going to be a plus 1. This is a plus 1. Last times last equals last. First times first equals first. What goes in the middle here is minus the product of these two guys. X times 1, x. So we learned that we have a 0 at 2. We have a 0 at 2 here. Let me get that guy put up. And we learned that we have a 0 at negative 1. And based on our discussion earlier, looking at this, I don't think we have any more zeros. In fact, I'm certain we don't. Now, you would say, well, what if this becomes 0? What if this becomes 0? In the event you get perfect cube, difference of perfect cubes, sum of perfect cubes. if we consider what those graphs look like, this is just this graph down 8. It only has 1, 0. This is this graph. This one is this graph up 1. It only has 1, 0. These will never give us another 0. So 0 here, 0 here, down through there. The only question that remains maybe is how high is this? So we could freshman graph, t-chart, maybe put a 1 in and see how high up we go. If I get a 1, 1 would give me -6 plus 7. Is that right? If I put in a 1, -6, or -1, excuse me, that was silly. -1 plus 7, 6, plus 8, 14. So we're going to go up to 14. Now, might we go a little bit higher? Yeah, there's no guarantee that 1 is the highest point there. It may be, we may get above 14, but that gives us a really good feel for what this graph looks like. And one more along that line. Same deal. We just want to take all the information we can do and try to do as little freshman graphing as we can. And some of the first things I recognize on this, this tells a big story about the graph right here. Positive, odd. Not an odd function necessarily, but odd degree polynomial. So rises to the right, falls to the left. Then goes through -32. Goes through -32. I have 0x. It goes through there with slope 0. Let me do that in red so it shows up. Goes through there with slope 0 for an instant. Then it wants to look like a positive parabola. This thing's looking like this. The next thing it wants to look like is a negative cubic. And so I'm not exactly sure what's going on with the wiggling there. I know there's a pull to try to bring this guy back down. Let's take a look at our zeros, because there could be some wiggling going on here. So zeros, if we set this thing equal to 0, well, it's not quadratic. It's not quadratic in nature. It's 4 terms. And if we have 4 terms, our best chance of finding rational zeros is to go ahead and factor by grouping if we can. So I note I can take out an x to the third. So I get x squared minus 4. Now, most people will then look at this and say, what can I take out? I do this. I say there's no use in factoring unless I can match that again. Wonder if I can get that. And if I can, this thing factors. So can I get x squared minus 4 out of this? Yes, if I factor out an 8. But that, I think, gives me some guidance what I'm looking for taking out. Okay, I've seen some people get confused with this before and wonder, how does this magically become x squared minus 4 times x cubed plus 8? And I would say, well, what if we had x cubed times a plus 8 times a? Can we factor that? And you would all recognize, sure, we can take an a out, and we get a times x cubed plus 8. Well, what if that was a? We can pull it out, just like we did here. Okay, so what did we learn? Well, we've got some more factoring to do. X plus 2, x minus 2. If you followed a slide or two ago, we know that the sum of perfect cubes factors, and it becomes an x and a 2. It becomes an x squared and a 4. This last times last has to equal last. That makes this plus, this plus. What goes in the middle here, I have to have a minus in there somewhere, is 2 times x. And if you paid attention on that previous slide, we know this will not deliver us any new zeros. Why? Because x cubed plus 8 just looks like this. Up 8. Okay, so what do we have? We have a 0 at -2. We have a pair, a pair of zeros at -2 and a 0 at 2. So a pair of zeros at -2, that's helpful. A 0 at +2. No zeros produced by this. Well, I got a pretty good idea what the graph looks like. Now, I know for certain on this, I'm coming up, I'm touching, and I'm dropping back down. We're not coming up again. End model behavior says we're going down over here. I know once I go through this and I just pass through this line, I'm heading up. The only thing that might be missing here is a little bit of our shaping in here. There may be some wiggling going on in there, but that'll be for a further discussion. That's a pretty good representation of what our graph looks like. Okay, I hope that was helpful for you, and we look forward to seeing you back at Purple Shirted Nerd.